Okay, welcome back everyone. We just not managed to finish the discussion of electrodynamics last time, so I think it will take me 10 more minutes or so. The last thing we had on the board was a Lorentz force, which I defined in general four-vector notation. And I then motivated this definition by showing that, first of all, this thing transforms in the right way under Lorentz transformation, and that for small velocities, so actually velocity equal to 0, it gives a traditional formula for the Lorentz force, which is very well experimentally established. So maybe this gives some good motivation to accept this as a general relativistic version of the Lorentz force. And then I've written it into space and time components separately. I think I have to write this again. So the 0 component, so the force was F with an upper index mu, and then I'll write F0, F1, F2, F3. And F0 turned out to be Q, that's the charge of the particle, over C. V dot E. V is the usual 3 velocity, E is the electric field, 1 minus V squared over C squared. And for F1, F2, F3, we found, let me see, Q over the root. And then E1 plus V2, B3 minus V3, B2. F2 Q over the square root E2 plus V3, B1 minus V1, B3, and F3 Q over the square root E3 plus V1, V2 minus V2, V1. Maybe you have realized that I had to read this from my paper. I did not know it by heart, but after having this on the board, I was able to write these two things by heart. And how did I do this? I just permuted the indices cyclically. Yeah? 1, 2, 3, 1, 2, 3, 1, 2, 3. It's always in the cyclic order. So if you have one component, then you can reproduce the other one easily. So now let's combine this with Newton's second law. This is the force. So the force is just the left-hand side of Newton's second law. Newton's second law, of course, a relativistic version. So this was F mu is dp mu by d tau. So F naught is dp naught by d tau. And I will now rewrite this equation, Newton's second law, with this expression inserted in traditional three-vector notation, so that we realize familiar expressions, or rather slight modifications of familiar expressions. So the first thing which I do is that I replace the proper time by the coordinate time, because in the standard formulas for the Lorentz force we don't have proper time, we have the standard time. So I write this by d by dt multiplied by 1 minus 1 over the square root. So that's d by d tau, right? And P naught, if you remember, was E divided by C. E is the energy. Don't confuse the electric field with the energy. The electric field has an error, or it has indices if I write it in components. E without anything is just the energy. And now I equate this with this expression here. So we have found that this is Q over C V dot E divided by the square root. And obviously this tells me how the energy changes. So this gives me dE by dt is what? So the C cancels, and I get Q times, there's no denominator, Q V dot E. So that's why the change of the energy with time is just the work. So that's the work done by electric field. So you see the magnetic field doesn't enter into this formula. So the magnetic field doesn't do any work. Well, this has something to do with the fact that the magnetic field produces a force which is perpendicular to the velocity. So it doesn't change the speed. It doesn't make the particle slower or faster. And that's the reason why it doesn't contribute to the work. So this is a traditional formula for the work. And the other three components I can combine into vector notation. So F with an arrow is just a vector with the components F1, F2, F3. And I can write this as Q root 1 minus V squared over C squared. And then I get here the E vector. And well, here I hope everyone recognizes the cross product, right? That's the first component of the cross product, V cross B. That's the second, and that's the third. So I get E plus. I think there's a problem with the factor C. Did I miss a C somewhere? Maybe just when copying. Oh, no. We have the other conventions. You know, there are several systems of units. In SI units, there's no C in this formula. So I think it's correct. We are using SI units here, and there's no C. So E and B do not have the same dimension, right? The dimensions of E and B differ by velocity. So the dimension of E is the dimension of B times the velocity. Okay, and we combine this now with, here I started with the second expression, here I started with the first expression. Maybe that's a bit confusing, but I now equate this to this equation here, which is just d, let me write it in this way, m ui d tau. Or let me do it in two steps. So combine with Fi, according to this formula, is the pi by d tau, and the pi by d tau is just mui by d tau, and ui is related to the standard 3 velocity by dividing by the square root by d tau. Okay, and now I can combine the two things in vector notation. Now I get q over root 1 minus v squared c squared, this vector expression. And now I have here also the standard velocity 3 vector, which I can write with an arrow without causing any confusion. d tau mv over the square root. Okay, looks familiar to the, in comparison to the standard Lorentz force equation, but it seems not to be exactly the same, and in fact it is not exactly the same. What we have to do in order to check this more carefully is we have to express the tau derivative by a t derivative. Remember, v is derivative with respect to t. Yeah? V is the standard 3 velocity. That's why we distinguish the letters v and u. U involves the derivative with respect to tau, v with respect to t. So v is just the standard 3 velocity. So we now get what? Q over the square root. E plus B cross B. Yes, so I have, well, first of all, I can take the m out of the bracket. We assume we have a particle with constant mass. And for d by d tau, I write 1 over the root d by dt. And then I have inside the bracket v divided by the root. And v is dx by dt. And here I have the root. Okay? So I have rewritten this in terms of d by d tau. And for v, I have inserted dx by d tau. And then I see that I can cancel the root here. And now we get the final formula for the Lorentz force equation. So the relativistic Lorentz force equation. And usually you write this on the left-hand side. So then we have m d by dt 1 over root 1 minus v squared over c squared dx by dt is q e plus v cross b. And now you see what's the difference to the ordinary Lorentz force equation, which you learned in your elementary electrodynamics course. There was not this square root, right? That's the difference. So the formula is different. So the standard formula for the Lorentz force equation is only an approximation. It doesn't hold for fast particles. And actually this is relevant. So for instance, for a synchrotron, you really have to take this into account. So if you try to operate a synchrotron with a standard Lorentz force equation without this term, then it doesn't work. For a cyclotron, it does work. Yeah, when Lorentz invented the cyclotron in the, I think, late 30s or so, he worked actually with the old Lorentz force equation, and he designed the cyclotron in order to work properly with this formula. And for the cyclotron, this is fine because he used sort of ions which are not so fast. But in a synchrotron, where you have electrons which move at a speed very close to the speed of light, then you have to use this formula. So that's a Lorentz force equation in 3-vector notation. And actually, the easiest way to memorize it is, of course, in the 4-vector notation, because that's much more compact. Yeah? And if you have this in your head, then you can, with a little bit of effort, you can reproduce this formula. Well, it's also not too difficult to keep in to learn by heart, but it's certainly not as compact and as simple as the 4-vector notation. So again, I hope this was an example which demonstrates that the 4-vector notation is really has some advantage in view of making formulas more compact. Okay, we will come back to the Lorentz force equation later when we do examples. So with this now you can calculate the motion in an electric field or in a magnetic field, for instance. You can consider motion in a homogeneous electric field or in a homogeneous magnetic field. And because of this term, you get results which are different from the standard formula, if the speed of the particles is close to the speed of light. Okay, so much for electrodynamics. As I said, we will come back to this. And the last section in this part on special relativity will be a few remarks on continuum mechanics. In particular, I have to introduce the energy momentum tensor, which will play a crucial role in general relativity then. So I will now talk for half an hour or maybe 45 minutes on continuum mechanics. And that will be the last part on special relativity. I think that's 2.7. So when we talked about mechanics, special relativistic mechanics, we considered particles, point particles. And we had to distinguish the two cases, that they are massive or that they are massless. So in the second case, we call them classical photons. And we had kinematic and dynamical properties for them. Now we want to describe a continuum, and that's actually very important for general relativity, because typically the sources of gravitational fields, which are discussed in terms of general relativity, are modeled as continua. So if we have a star, we model this as a fluid. The interior of the star is usually modeled as a fluid. So it has a density and it has a pressure and things like that. That's the model we make for the star. And also in the cosmological constant, when I want to make a model of the whole universe, then we very frequently model the matter in the universe as a fluid, or even as a particularly simple fluid, as a dust. And the idea is to treat the individual galaxies like the particles in the gas, and to replace the motion of the individual galaxies by a mean flow, which is then called the Hubble flow, which is treated like a fluid. So we think of the universe filled with a fluid, and this is just an abstraction, an idealization of the real matter, which is clumped into galaxies and galaxy clusters and things like that. So these fluid models play a very important role as a sources for Einstein's field equation later. So typically one uses these fluid models for sources in an astrophysical context. So that's the reason why we have to talk a little bit how we describe such continua mathematically. So I will first do it in special relativity, and we will then very easily transform this into general relativity later. So the idea is that we have a fluid, which, well, for the time being, you may think of a fluid here in the laboratory. Yeah? So on the table, there's a container, and in this container, there's a fluid, and we want to describe the motion of the fluid. So it's swirling around in a certain way. How would we do this in the context of general relativity? So we describe the motion of a material continuum. And material continuum is just another word for what you would call a fluid. And, well, of course, in traditional terminology, it would have a velocity field. But now we are doing this four-dimensional formalism, so we will assign a four-velocity to it. And that will be the mathematical object which describes the motion of the fluid. So we describe it in terms of a four-velocity field. So what is this mathematically? It's a four-velocity. So I now, for this four-velocity field of a continuum, I use a capital U. Yeah? I had the little u for the four velocities of particles, and I will use a capital U for the four velocity of a continuum. And because now it is a continuum, it fills all of space-time, or at least the volume in space-time continuously. It will depend on all four coordinates, x0, x1, x2, x3. And because it is a little bit long, I will in the following just write u mu of x. So if I write the argument x, I mean all four coordinates. So this is an object which describes the motion of a fluid. And, well, so if I draw a picture, x0, x1, x2, as usual, one of the spatial coordinates must be memorized. It cannot be shown in the picture. Then I have such a four vector at every point. At every point, I have such a four vector. So if I integrate this up, I get flow lines, right? And these flow lines tell me how the fluid moves. So if they come closer together, this means that the particles may make a motion like that. Or if they have a spiral shape, this means that the particles move around in circles. So that's how we model a fluid. Question is there any restriction on this? What do you think? Should we restrict this four vector by any condition? Or can it be any vector? Can it this, or this, or this? Question to the audience.
It should be time-like.
Yes, very good suggestion. Yeah, I think it should be time-like and future pointing, right? So if I draw a light cone here, then it should point into the future cone. Well, which half I call the future or in which half I call the past is a convention, right? If I have done it once and I have the vector pointing in one half at one point and assume that it is continuous, then it must point into the same half everywhere. So if I assume continuity, it's just sufficient to say that it is time-like. So I write this in the form with that the condition for being time-like was that this here u and ux is negative. And we had this convention that whenever we have a four velocity, that we normalize it just in order to remove this freedom of stretching it or shrinking it. So we normalize it to minus c squared. So this means if we have an observer who lives on one of these flow lines, such observers are called co-moving observers. Yeah, if I assume that there's an observer who moves on one of these flow lines, and we assume that the forward velocity of the observer at any point is exactly the same vector as that for the fluid, then it means that the observer uses proper time, right? So this condition is a condition that the parametrization of the flow lines is with proper time. So that's the forward velocity which describes the motion of the material. So if I write this u mu in any inertial system, then of course it has the usual form, like any forward velocity has, but now it is a field. It's a function of all 4 coordinates. That's a new feature. Yeah, up to now we had world lines, which have a tangent vector field which is given along this world line. But now we have a whole continuum. So we have the forward velocity at every point of space-time. So that's what describes a fluid. But apart from this difference, it has exactly the same expression as the forward velocity always has. So the 3 velocity v is now, of course, also a function of all 4 coordinates. So in traditional notation, this means it depends on time and on x, y, and z. And the components are, as you hopefully remember, c, v1 of x, v2 of x, v3 of x. So this gives me the relation of my forward velocity field u mu with the traditional 3 velocity. So this 3 velocity gives me really the motion in the inertial system in terms of the traditional 3 velocity. If I'm sitting in this inertial system where my u mu takes this form, then this tells me what is really the velocity of the fluid, the traditional 3 velocity at any point at any time. Yeah, time and all 3 spatial coordinates are combined into this x here. So maybe I should write this down. So v of x is a 3 velocity. Well, if you just say velocity, then you mean the 3 velocity of the fluid in the inertial system. Of course, this changes from inertial system to inertial system. I can make this v equal to 0 at any one point, but usually only at one point. So for instance, this thing I've drawn here, at this point, I think the velocity would be 0, right? The tangent vector looks very much vertical. So if it is perfectly vertical, then this means that at this point, the 3 velocity vanishes in this inertial system, which I've used here. But in general, I can do this only at one point, because my fluid will have quite different velocity vectors at different points, right? So there's nothing like a universal rest system for a fluid in the context of special relativity, where we consider only inertial systems. So you can introduce something like a rest system at one point, but not for all points simultaneously. This would mean that at this point in the 3-dimensional picture, the velocity vector would be 0. This means this fluid particle would stay where it is. Yeah? So you would get something like this here. It's now in 3 space. You would get something like this, for instance. So that's your v of x. In general, it is time dependent, so the pattern will change. And here at this point, you will have, well, what I had in mind was this here, something like that. So at this point, you would have v equals 0. This means your inertial system is a rest system for this particular space-time point. Yeah? You could go to another inertial system just by moving with this 3 velocity. Then this point would become the point where the v has a 0. This would be the rest system at the neighboring point. So in this way, this forward velocity describes a fluid. And now we will discuss what we mean by the energy density. So the first quantity which characterizes a fluid is a forward velocity. And the quantity which will be very relevant for relativity is the energy density. Because, well, I can say this already now. In standard gravity, by that I mean Newtonian gravity, the source of the gravitational field is a mass density, right? I must have a mass, this produces a gravitational field. Now relativity has taught us that mass is but a special form of energy. So it should not come as a surprise that in general relativity, any form of energy is a source of a gravitational field, not just masses, any form of energy. So the energy density will be the source of the gravitational field. The energy density will be on the right-hand side of Einstein's field equation. Yeah, in the same way as the charge is on the right-hand side of Maxwell's equation. So that's the reason why the energy density is a quantity which is very, very relevant for us if we want to do general relativity. It will be the source of gravity. And the question is, how do we describe the energy density of such a fluid? So that's a somewhat non-trivial question, so it will keep us busy for a few minutes. Should I continue here? No, I think I do this here. So how do I write this? So introduce the energy density. I will denote it by epsilon of x. Obviously, it will depend on the space-time point, right? So at a particular time and at a particular space point, I will have a certain energy density, and at other points, I will have other energy densities of the fluid. So how do I do this? Well, if I want to know what's the energy density here at this point, now in this moment, what I would do is I would consider a very small volume element around this point. Then I would measure the energy which is inside this volume, and I would divide it by the volume. That would give me the energy density, right? So I write this down in words first, and then we see how we can translate this into formulas. So this should be something like energy divided by volume. And energy, well, we know already that there are different forms of energy. And here for our fluid, well, what would be the energy? So this would certainly contain a part which is the rest energy. Then, of course, the fluid particles will move around, so they would have a kinetic energy. Kinetic energy. Yeah. What do you think? Is this all, or is there an additional term? What do you think? Is it just rest energy and kinetic energy, which is in such a ball of a fluid, or anything else? Well, I'm very strongly of the opinion that in general there will be another term. Namely, this will come from the interaction of the particles. Yeah? If I think of particles inside this volume, they will interact in a certain way. And this interaction will give a contribution to the total energy. So it's not just the motion which makes up the whole energy, the rest energy and the motion. There's also something coming from the interaction. Yeah, in Newtonian physics, we describe the interaction usually in terms of potentials. So you know, if a particle is interacting with something, it has not just the kinetic energy, it has also a potential energy, right? So the interaction will also enter in some way or other. So let me just vaguely write here interaction energy. Interaction, energy. And I divide this by the volume. So that's roughly the idea what makes up the total energy. I should write this either every time with a capital letter or every time with a lowercase letter. So this was the first question, what the energy might be made of. And we will then translate this in a minute into formulas. The second question which arises is this really a scalar invariant? So what I've just told you, this procedure, consider a volume element, measure the energy, divide it by the volume, and call this epsilon of x. Does this give you a number which is independent of the observer, which is just a scalar invariant, which characterizes the fluid uniquely? Or would it depend on the person who is doing the measurement, or the reference system in which the measurement is done? What would you think? Well, look at the expression, energy and volume. Are energy and volume, are these invariants, or do they depend on the observer? We have discussed this to some extent. Let's begin with the volume. I think that's quite obvious. We are doing special relativity. It's a volume invariant. If I measure the volume in one inertial system, somebody else measures it in another. So it's the same material volume, yeah? Considered by one observer here and then by one who moves in this direction. Do they measure the same volume, yes or no? I think everyone should know this. So you are shaking your head. Why is it not the same? What's the phenomenon? Yeah?
Contradiction.
Yes, exactly. Yeah. So in the direction of the motion, you have the length contraction. And in the other direction, you have nothing. So in this direction, the volume shrinks. So it is not an invariant. The volume is not an invariant. What about the energy? Is the energy an invariant? We have discussed energies of particles. Yeah. Yeah, it's not an invariant. Remember, it was one component of a 4-vector, which transforms on a Lorentz transformation. We have calculated this for photons. This has given us a Doppler formula. Yeah? The Doppler formula is a formula which tells us how the energy changes, the energy of a photon, changes if I go from one inertial system to another. So it's not an invariant. Well, of course, this could be that the quotient is an invariant. Yeah? It could be that the two things depend on the observer in a way that the dependency cancels. But actually, that's not to be expected. So we would expect that the quantity depends on the observer. And that's actually what will come out. And we will calculate now how this depends on the 4 velocity of the observer. So that's the question we want to answer. How does epsilon of x depend on the 4 velocity of the observer? Actually, that's fairly easy to calculate for a special case. And I will consider the special case first. And the special case is a case where I do not have an interaction energy. Yeah? So if we have a fluid in quotation marks where the individual particles do not interact with each other. So they are just moving around. And each individual particle is moving in a way as if the other ones would not be present. Yeah, they do not influence them in any way. So they do not produce anything like a pressure onto each other or something like that. They do not attract or repel each other. They are just moving as if the other ones would not be there. Such a medium is called an incoherent fluid. Or in particular in the relativity community, we call it a dust. So in cosmology, if you make for your flow of galaxies the model that there's no interaction between the galaxy, then you would say I make a dust model of the cosmos. Yeah, that's a standard terminology in relativity. So we consider this case first. And that's actually the simplest case. Consider the simplest case first. And that is what we call, that is characterized by the fact that we have no interaction energy. Of course, this would be a very poor model for a star. Yeah, if you assume that there's no interaction between the particles, well, it would be a model for a collapsing star. Yeah? It would immediately collapse under its own gravity. So for stars, of course, the pressure does play an important role. So no interaction energy, and that's what we call an incoherent fluid. Incoherent fluid. The plasma people also sometimes say cold fluid, but I don't like this expression particularly, so I don't write it down. And what we relativists usually use is the word dust. Well, and then we can write this quotient fairly easily. So let me do this. I need a little bit more space for this. So the picture is this. I write this in an arbitrary inertial system. So I fix a point x, and I want to calculate this epsilon at this point. So I have an inertial system. So I have here an x0 axis, here x1 and x2 axis. Let me shift this point a little bit upwards. And here I have my forward velocity of the fluid. Of course, it will not be vertical in general. So it will be something like this. And then I have the forward velocity of an observer which is at rest in my inertial system. And I denote this by little u. It does not depend on x. Yeah? The little u is the same everywhere. Yeah? It's just the forward velocity of an observer which is at rest in my inertial system. So that's not x dependent. This is x dependent because my fluid will move around in a certain way. And so in this coordinate system now, my u nu has the coordinates c 0, 0, 0, right? That's 4 components which characterize a little u. And my big U will have this general expression. So it will be characterized by a 3 velocity v. So it will be something like 1 over 1 minus square root, which depends on x, v of x, c squared. And here I have c v1 of x, v2 of x, v3 of x. And for later purpose, I will calculate the expression eta mu nu, u nu, u mu of x. Well, that's easy, because here I have 3 zeros, so the spatial terms give nothing. So I just get minus, that's eta naught naught, minus c squared divided by the square root. Minus c squared divided by the square root. Okay, so this was a preparation. And now I write down my epsilon of x. So epsilon of x was something of this sort. Energy divided by volume. So let me denote the energy by E and the volume by vol. So E is what? Well, I have a little volume element around this point, and I want to know what is the energy inside this. And we remember the energy is just up to the factor c, the zero component of the form momentum. And we had expressions for this. And we found that the energy for an object with total mass m is given by this expression, 1 minus v squared over c squared. This was the expression we had found for the energy. Remember, we made this Taylor expansion, then the zeros order term just gives the rest energy, and then comes the traditional kinetic energy, m half times v squared, and then comes the higher order terms, which go with v over c to the fourth, and so on. So that's the expression for the energy we have. And now you see why I have calculated this expression, because it's exactly the thing which we have there. So if I now replace c squared by the square root by this expression, you see that this is just minus m eta mu nu u mu u nu. Okay? So that's the energy. And the volume is what? Well, how would I calculate this? I would consider a piece of the fluid here. And then I would calculate the volume. Well, I want to know the volume in my inertial system. So this would be this here. Maybe I should do it a little bit bigger. I think you cannot see this from the back. So I consider, actually it's supposed to be a very small volume element, but I draw it a little bit bigger so that you can see something. So it's something like this. Yeah, so these are the flow lines of the boundary of my volume element. So that would be the volume. Yeah. So that would be a 3-dimensional cross-section through this world tube, which is made up by my volume element. And if I measure the the length, the height, and the width of this thing, then I get the volume. So this is perpendicular to the little u. That's a little u here, u. And now I have something like the volume element in the rest system. So that would be perpendicular to this here. So this angle here is the same as this angle here. Then this gives me the volume element, the volume in the rest system. I denote this by all divided with an index 0. And we remember how the two things are related. This is just length contraction. Yeah, this is something times the volume element in the rest system, and the something was just the square root. Wait a minute, this is in the numerator or in the denominator. It's length contraction. This thing should become smaller. So this is small, so it should be in the numerator, right? This is smaller than 1. So this is smaller than this. So I think that's the correct version. And again, I get this square root. So I can express it by this term here. So I get a minus sign. I get the volume element in the rest system. And then I get the square root in the numerator. So this is c squared divided by eta rho sigma, rho sigma u rho u sigma. Okay? If I take this here, yes, I think I got everything right. And now I can take the quotient. So epsilon depends, actually everything depends on x. I've dropped the arguments here. So this was a quotient, E divided by the volume element. So it is this divided by this. So the two minus signs kill each other. Then I get m divided by the vol 0. And then I get a c squared. This is, it's down. That's funny. Did I make an error with the c squared? Okay, let me see what we get. I think the c squared is wrong here. But I get it if I take this expression seriously. And then I have this here. And this also comes into the numerator. So I get two times this term. So I get eta mu nu, u mu u nu. And then I get eta rho sigma u rho u sigma. I think the c squared is wrong. Do I have it here? No c squared here. Does anybody see where I messed up the factor c squared? Check the dimensions. So this is a c squared. One c squared cancels, and the other c squared. M times c squared is an energy. That's fine, and volume is a volume. I think the units are correct. Maybe the c squared is correct, and I made a mistake here in my calculations on the sheet. Yeah, okay. I never know where the c's are, as I told you already, because for my own calculations, I usually set c equal to 1. So for the moment, let's assume this is correct. So what have we found now? Well, first of all, I should have said, no, it's definitely correct. It is. Let me see. Rho. Yeah, the units are correct, right? This has the units, the same units as c squared. It's a velocity squared. So this goes away against this. And then I have another velocity squared. M times velocity squared is an energy. Energy divided by volume is energy density. Yeah, I think it's correct. Okay, so let's trust that this is correct. So what is this here? Let's call this mu. This is obviously it's the mass of the thing, and mass always means rest mass for us. This was our convention. And it's divided by the volume in the rest system. Yeah? So it is the mass density in the rest system. Mass density in the rest system. So, I'm sorry?
Maybe take another letter for that, as we may mix it up with unity.
Oh yes, yeah, but actually I want to call it mu for the rest of the term. Yeah, maybe I should change the summation index here. So let's call this lambda. Yeah. Well, some people use rho for the mass density, but I want to use rho for the charge density. And there may be occasions where the two things occur at the same time, and then we are really really confused. So I would like to stick with mu. So I try to avoid the index mu in formulas where the mass density occurs. So let's summarize this. So we have found what? So we have found that epsilon of x is let me write it in this way. It's something which I call T mu nu of x. I wanted to avoid the mu and mu. So let's write alpha and beta. U alpha, mu beta, with T alpha beta, which depends on x, is what? Well, it's a coefficient here. So if we omit these two things, what do we get then? We get the mu, which of course will depend on x, right? The mass density will depend on x. Then I have a 1 over c squared here, which confuses me a little bit because I don't have it in my notes. And then I have n eta lambda nu. Well, the indices are now alpha and beta. So it's eta alpha, say gamma, u gamma of x. And it's eta beta, I don't know, lambda, u lambda of x. And of course, with our conventions of raising and lowering indices, we can write this in a more compact form. It's mu divided by c squared u alpha of x, u beta of x. Okay? And that's the formula I wanted to derive. So we see that the energy density is a quadratic form in the four velocity of our observer. Yeah? So we had discussed that we do not expect it to be independent of the observer chosen, and now we see in which way it depends. It depends quadratically. And actually this should not come as a surprise. If you think of energies of objects which are moving around, you would expect them to be quadratic in the velocity. Think of the standard kinetic energy. Yeah, it's m12v squared. So there should be something like a quadratic expression be involved, and that's what we get. So the energy density is characterized in an observer-independent way by this object which is here, which makes up these coefficients. And for a dust, it has this form. We have calculated that it has this form. So it's combined of the mass density and the four velocity of the fluid. And this thing, because it gives the energy, and well, also the flow of the energy, which is related to the momentum, one calls this the energy momentum tensor. Now at the moment, I will not explain what a tensor is. So at the moment, we may just assume that the word tensor is another word for a thing with two indices. Yeah? So something which can be arranged in a matrix, which depends on two indices. At the end of next week, we will start developing the mathematical apparatus of general relativity. And then I will precisely define what a tensor is, and we will learn tensor calculus to some extent, to the extent as it is actually necessary. So at the moment, this is just, it just tells that the thing has two indices. So I could call it the energy momentum matrix, but this is not the usual terminology. So the usual terminology is to call this. So this here is being called the energy momentum tensor. Actually, it's a tensor field. Yeah, it depends on x. So I should say energy momentum tensor field, but usually one just calls it the energy momentum tensor. And we have calculated for dust. Of course, it is true only for dust, right? Remember, we started by using this formula for the energy. And this is not true if there's an interaction, if there's a contribution from the interaction, right? This is just kinetic energy. Relativistic energy, which is made up of rest energy and kinetic energy. So this is only true for a dust. So that's the energy momentum tensor for a dust. So this, we can say the energy momentum tensor is a thing which gives us the energy density for any observer. We just have to multiply it with the forward velocity of the observer twice. Then we get the energy density. So that's a property which characterizes the energy momentum tensor. Obviously, it is symmetric. Yeah. So 2 remarks. So the first remark is T mu nu is symmetric. By that I mean I get the same thing if I interchange the indices. Well, actually, if that's the equation which characterizes the energy momentum tensor, then we see that an antisymmetric part would drop out, right? Because this here is symmetric. So if it would have an antisymmetric part, it would give no contribution to the energy density. But from this expression, we see that it already is symmetric. That was the first remark. And then the second remark, I think I need a little bit more space, but I begin here. So the energy density is produced by summing over both indices with the forward velocity. There's also something interesting going on if I sum only over one index with U alpha. So if I introduce a thing which I call S alpha, and this is formed in the way that I consider T alpha beta U beta. I've written it here with an upper index. You could also write it with lower index. You just could pull this down and change the betas as you like. So you can write any combination you would like to have. I've written this here. This here is called the energy current or energy flux. Let me write current 4 vector. And why is this? So let me explain this a little bit. With respect to U, yeah, with respect to, let me squeeze this here. So that's not an object which characterizes the fluid in an observer-independent way. It depends on the forward velocity of the observer. Energy current 4 vector with respect to U. To U mu. Yeah, to the observer which has this forward velocity. And why do we call this energy current? Let me explain this. Okay. Let me write, so the S has an index alpha, which takes value 0, 1, 2, 3. Let me write the temporal and the spatial component separately. So what is this? The S naught is T naught alpha U alpha, which is mu. Here I have mu over C squared. So, and then I have the capital U naught U alpha times the little alpha. And if you remember, this was, it's still on the board. This here is just minus C squared over the square root. Oops. And the U naught was C over, and I have this C squared here. And U naught was C over the square root, so I get the square root squared. So I have this expression, which is, I have again problems with the C's. So let me check. Mu, oh, so this would cancel. I have mu times C. Mu times C squared would be an energy density. I wanted to have the energy density, but again I have a factor C wrong. So these factors C really kill me. So this is, let me write it. It should be precisely the energy density, but I get it up to factor C. So apparently I have again messed up somewhere the factor C. By the general structure you see, right? If you have mu times C squared, that would be divided by this term. This would be precisely the energy density. But a C is missing. Okay, and SI, let's see, what is SI? The spatial part, that is mu over C squared. Again, U naught. And, no, what, UI. UI. U alpha, and this gives minus C squared again over the root. And then I have the UI, I have another C squared. The UI is VI over the square root. And again, I had the wrong dimension. What I wanted to get is the energy density times the velocity in terms of C. And there's again a C missing. But this is the spatial energy current, again up to factor C. So you see it has a direction in which the fluid flows, and in our case the fluid is just the dust, so the energy flow is proportional to the motion of the dust. There's no other energy than just the kinetic energy. So it really points into the direction in which the energy is flowing. And here, if I correct this C here, then it also has the correct dimension. So what I wanted to demonstrate is that these quantities are quite analogous to the rho and the Ji, which we had in electrodynamics. But now, not formed with the energy, but not formed with the charge, but rather with the energy. So this thing is the same expression in terms of the energy as the rho and the Ji is in terms of the charge. So that's the reason why we call it the energy current. Yeah, as we call it the J mu, the charge current. So that's analogous. Oops. Analogous to J mu, which composes into rho and Gi in electrodynamics, what we had in the last lectures on the board, on the right-hand side of Maxwell's equations, right? There was a charge density and the spatial charge current, which gives the space-time, the four current of the charge. And in the same way, this is the four current of the energy. So the analogy is that we interchange charge and energy. So for the charge, we had the continuity equation. Charge was conserved. So now the question is, do we have a similar thing for the energy? Should we expect that also the energy is conserved? What do you think? If you have such a fluid, would you assume that for the energy there's a conservation law analogous to the conservation law of the charge in electrodynamics? So charge cannot be produced. Yeah? There's an absolute conservation law for charge. There's no exception known until now. So that's what we have at the moment. What about the energy? If we have a fluid, we have assigned an energy to it, and we now consider the current, which is analogous to the current of the charges. And the question is there also a continuity equation for this current? Would you expect this? So would you expect energy conservation to hold for the energy of this fluid? Under any assumption. The energy of a fluid, is this conserved always? Well, of course not. Of course not. If I do something with a fluid, if I act on it from the outside, if I provide forces onto it, of course the energy would change, right? If I go with my hand into the fluid and swirl around, and of course I change the energy content of the fluid. So of course the energy in general is not conserved, but it will be conserved if it's a closed system, if I leave the fluid alone, if I have no interaction with anything. So for a closed system, I would require that I have a conservation law analogous to the conservation law for charge. So for closed system, one would require conservation of charge. It's a conservation of energy, sorry, conservation of energy. This means a continuity equation which has exactly the same form as a continuity equation for the J, now with the S. And this was the equation, d mu S mu is 0, right? And now let's see how this translates into a property of the energy momentum tensor. So if this holds, then we can write it in this way. We can write it in this way. So d mu of S mu, that's something where I differentiate a function which depends on the 4 coordinates, and that's supposed to be 0. And now what was the S? The S was introduced, it's down there. It was introduced as T mu, say, nu of x u nu, which does not depend on x. Yeah? The u nu is here is still the picture. It's a 4 velocity of my inertial system, and that's the same at every point. So I would get something like d mu t mu nu of x, and the derivative does not act on the u nu. And this is supposed to hold for all allowed 4 velocities. So for all possible velocities of my observers, this means for all little u's which are inside the cone. So this has to hold for all u nu with eta mu nu u mu u nu is minus c squared. And of course, this can hold only if this here is 0. So then we have d mu nu of x is 0. And that's the conservation law for energy in relativity. So for a closed system, that's a sort of a divergence, right? Here's the summation over the index with respect to which the derivative is done. So one calls this the divergence of the thing, although it is not a vector, it has an additional index, right? So one says that in special relativity, the convergence of the energy momentum tensor, the divergence of the energy momentum tensor for a closed system is 0. So that's this famous conservation law, which will play an important role when we try to guess the right form of Einstein's field equation. So we have worked this out. this energy momentum business for a dust only. Yeah, that's the simplest case. And for this case, we were able to write the form of the energy momentum tensor explicitly. Other systems, of course, have more complicated energy momentum tensors. We will do an exercise for the next most simple case, which is a perfect fluid. Yeah, a perfect fluid has, in addition to the mass density, also a pressure. So it's characterized by two scalar functions. The dust is characterized just by one scalar function. And then there are more complicated media where you introduce viscosities and things like that. Yeah, and you can do arbitrarily complicated matter models. But for general relativity, for most applications, actually, the dust and the perfect fluid is fine. So far for dust. Yeah? Until now, we haven't talked about anything else but dust. So I make a few general remarks about other media. For other media, we have an energy momentum tensor of more complicated form. Complicated form. But the general features which carry over are the following. So the general features are the first thing that this expression, whatever the energy momentum tensor for this particular medium is, I've written it with lower indices. Let's stick to this. U sigma gives the energy density. Yeah, whenever somebody tells you the energy momentum tensor of the particular medium he wants to describe, you can calculate the energy density with this formula for any observer. So the book by Miesner, and Wheeler, which was one of them I recommended to you, they used to say the energy momentum tensor is a machine with two slots. That he is referring to these two, to the possibility to multiply it in two places. And if you put in both slots the four velocity of an observer, then it gives you back the energy density of the medium. So that's how you may think of the energy momentum tensor. So that's the first general feature. The second general feature is for all we are doing, we will assume that the energy momentum tensor is symmetric. You see, if this is a defining property, then an antisymmetric part would give no contribution, right? It simply drops out from this equation, because if I multiply something antisymmetric with something symmetric, I get 0. So it's a very natural assumption, let me put it this way, to restrict to symmetric energy momentum tensors if you use this as a basis. And then we have a couple of more assumptions. One usually imposes on reasonable energy momentum tensors. So for instance, one poses that T mu nu of x, mu nu, u sigma should be non-negative for all u nu with eta mu nu u nu is minus c squared. This means that the energy density should be non-negative. We discussed this already on Wednesday in the tutorial. Some of you asked me what happens if I have negative masses in a relativity, and my answer was, a lot of things break down. Yeah? In relativity, we usually assume that energies cannot be negative. So if we would have something which would give you a negative energy, then a lot of things would break down in relativity. So one usually assumes this, that a reasonable energy momentum tensor should give you something which is not negative. The one for dust certainly does this, provided that the mu is non-negative. Then it's obvious that the energy density which comes out here, because it's a square, because it's a square, it cannot be negative. So that's what one calls the weak energy condition. And most people adopt this for reasonable matter. So I would say if you give me an energy momentum tensor which violates this condition, then it's not a reasonable model. Actually, as I just see Maciej, who likes wormholes particularly well, so wormholes are things which have an energy momentum tensor which violates this condition. So if you believe in the existence of wormholes, then you must believe in the existence of matter which violates this energy condition. So at the mouth of a wormhole, you would need something with negative energy. That's the reason why many people think that wormholes do not exist. But that's a matter of debate. So, and another condition which we have, where we had here introduced this energy current. This tells you how the energy travels. It gives you a 4 vector which characterizes the motion of the energy. And of course, energy can be used as a signal, right? So if the energy flows from my position to your position at a superluminal speed, then it would have this violation of causality we have discussed. So it would require that this thing should not lie outside of the light cone. So this S should be inside the light cone. So you should have that S mu of x, which was defined as T mu nu of x. Your nu should be, well, it should be either time-like or light-like. Yeah, it should be either inside the cone, then the energy moves with subluminal speed, that's fine. Or it should be on the cone, that's also allowed, that the energy moves at the speed of light. But it should not be space-like, it should be non-space-like. And again, for all u nu with eta mu nu, u mu u nu is minus c squared, and that's what people call the dominant energy condition. And again, most people would say if you have an energy momentum tensor which violates this condition, then it's not a physically reasonable one.
Is it correct that the indices for the energy density are different, the lower and upper indices?
Which equation you are referring to?
The first dot.
The first dot. Oh, of course not. Sorry. That's just a writing mistake. So I should either make the mu into a sigma or the sigma into a mu. Sorry for this. So let me write it this way. Are the other ones correct? Mu nu, nu mu. Here's also wrong. Same thing. Mu, mu, nu. Okay, we'll play a little bit around with energy momentum tensors in the worksheet. But I should make a remark that energy momentum tensors can be introduced not only for fluids. Yeah, we have here continua which have a certain 4 velocity and move around in this way. They can assign to all sort of fields. Also, the electromagnetic field has an energy momentum tensor. Yeah, it just gives the energy of the electromagnetic field itself, not of the charges which produce it, but rather of the field itself. Or if you deal with the Dirac equation or with the Klein-Gordon equation, they also are associated with an energy momentum tensor. So you can associate this with any field. It's a general feature of field theory. Okay, so we have now a rough idea what an energy momentum tensor is, and this will play an important role when we talk about Einstein's field equation. And with that, I can now leave special relativity. And we have 15 minutes left in order to start thinking a little bit about how to move to general relativity. So I call this section heuristic approach to general relativity. What I want to do is just review a little bit what people thought in the time between 1905 and 1915. This means between special relativity had come into existence and general relativity would come into existence. What people had thought, how gravity could be treated in the context of relativity, and why the obvious and close at hand solutions did not work, and why something completely new had been done, which was then called general relativity. So if we summarize what we have discussed until now, then it was the following. We had introduced a new space-time theory. So the new concept of space-time was the special relativistic space-time, characterized by these postulates P1 and P2. And then we have seen that virtually all of physics, the parts we discussed, fits into this scheme very well. In particular, electrodynamics fits extremely well. We don't even have to modify Maxwell's equations. The way they were before, they fit perfectly well into the new space-time theory. And actually now one understands much better what's going on with Maxwell fields as before. With other things, with mechanics, we had to modify the theory a little bit. And these were always modifications of the sort that the old equations were reproduced for small velocities. For big velocities, something new was found. And well, everything was in agreement with the experiment. So this was also fine. And one body of a physical theory which was not included until now is gravity. And of course, that's an important thing. And obviously, as soon as Einstein had finished his theory, he started thinking about how to include gravity. And this was something which turned out to be a hard nut to crack. So we will now briefly discuss why it is so much more difficult to include gravity into relativity than the other things. Heuristic approach to general relativity. So the obvious attempt is that we try to include Newton's theory of gravity, which was an excellent theory. Yeah? It has explained so many things, the motion of the planets, and actually, up to now, people use this theory to fly to the moon, and they arrive, they want to arrive. Yeah? So it's a very, very good theory. So try to include Newton's theory of gravity, maybe with some modifications for high velocities. You would expect maybe something of this sort. This would not come as a surprise. Into special relativity. And we will now discuss why this doesn't work, why we need something new, which is then called general relativity, in order to have a theory which describes gravity. So what is Newton's gravity? Newton's theory of gravity consists of two parts. So I have the field equation. The field equation in traditional notation reads Laplace phi is, I think I have 4 pi g. There are again different conventions. 4 pi g, yes. 4 pi g times mu. So what are the symbols? Phi is the gravitational potential. In Newton's theory, the gravitational field will be described by potential. Mu is the mass density. What else do we have? G is the gravitational constant. Newton's gravitational constant. I emphasize this because very soon we will introduce something which is called Einstein's gravitational constant, which differs by a certain factor from G. Newton's gravitational constant. And yeah, what else do we have in the equations? The Laplace operator, of course, but I think everybody has guessed what I meant by this. So that's the Laplacian. So that's the field equation. Yeah? If you tell me where the mass densities are, how they are distributed, then this differential equation combined with appropriate boundary condition tells me what the gravitational field looks like. And then we have the equation of motion. So this is just the inertial mass, d2 x dt squared, is the gravitational mass times the gradient of the phi, and I think the usual convention is to have a minus sign here. Minus gradient of phi is a gravitational acceleration. And here the symbols are the following. So x is, well, x, which is a function of t, is the trajectory of the particle. Which I throw into my gravitational field. And this equation gives me the equation of motion for the particle. M is the inertial mass. Ms, well, S reminds of the German word schwer, schwere Masse in German. In English, I say it's called the gravitational mass. So you would more likely use the index G, gravitational mass. And what else do we have? Yeah, del is, of course, the del operator. Yeah, it's dx, dy, dz. So these are the two equations. Now let's look at these two equations. Do they fit into special relativity? Well, some of you are maybe surprised that I distinguish M and MS. Yeah? But in Newton's theory, there's actually absolutely no reason to assume or to expect that there's any relation between the two things. They're introduced in a completely different way. That's the inertial mass, which gives the resistance against acceleration. So it describes how inert I am, how strong my resistance is against effects which are imposed onto me. And this is something which tells me how I react to a gravitational field. Yeah? How strong I feel a gravitational field. So that's conceptually two completely different things. And now, from the Newtonian point of view, as a complete surprise, one finds from experiment that the two things are the same. Well, actually, more precisely, one finds that the quotient of the two things is a constant of nature. Yeah? For any body you take, the quotient of the two things gives the same value, the same constant. And then you can use the same units for both. Yeah? Then the quotient becomes 1, and you can identify the two things. That's a complete surprise. There's no reason in Newton's theory why it should be that way. And yeah, as I said, you can just observe this as a surprise. So Newton's theory would work perfectly well if M and Ms would be different for different particles. Yeah? If they were completely unrelated. And actually, this will be an important observation when we move to general relativity, because in general relativity, it is not a coincidence. It's built in from the start that it must be this way. General relativity, we could forget about general relativity if the gravitational mass would not be the inertial mass. Yeah? We could forget about the theory. It had no chance to work. So it's really based on this assumption. But in Newtonian theory, that's not the way. So that was the remark why I distinguished these two things here. So now let's look at the two equations. Are we in the same lucky situation as we were in with electrodynamics, that the equations automatically fit into special relativity, that we don't have to modify them? Well, obviously not. Look at this equation. Do they have a chance to be Lorentz invariant? Look at this equation. You don't have to do any calculation. Just at first sight, I think you see that this cannot be Lorentz invariant. Why is it? Lorentz transformations mix x and t coordinates. Yeah? So if something in one coordinate system does not involve t derivatives, like this operator does, and now I move to another inertial system, then t derivatives would come into the game. Yeah? So it's obvious, without doing any calculation, that this thing is not Lorentz invariant. So it cannot be Lorentz, the whole setting cannot be Lorentz invariant. So the equations must be modified. So has anybody an idea how the equations could be modified so that they become Lorentz invariants? What sort of modifications would you suggest? I think if you look at the first equation, there's a very natural idea which jumps towards you when you just look at it. Any idea? So I said that the problem is with this thing, that it only involves partial derivatives with respect to the spatial coordinates. Or there's an obvious modification of this operator so that it involves also time derivatives. What would this operator be? We had it already on the board. wave operator. Yeah, I think that's the first idea. If you start thinking about this problem, the first idea which comes to your mind is to replace this by a wave operator. There's also a more intuitive argument why doing this. Well, not asking about Lorentz invariance, just looking at the fact that here, if I move the mass densities, yeah, if I juggle my masses a little bit, because I have no time derivatives here, this would be felt by the field immediately. Yeah? So the gravitational field, which is produced by this mass, would change immediately there, far away, if I move my masses a little bit. That's an obvious contradiction to the fact that, according to special relativity, superluminal velocities are not allowed for signals. I could send a signal just by moving a mass here, and you measure the gravitational field back there, and we have a signal which travels with arbitrarily large speed. Yeah? If you replace this by the wave operator, then we know how waves propagate. They propagate with c, yeah? If it's the usual wave operator. So then the signal would propagate with c, and everything would be fine. So also from this point of view, it's a very natural idea to examine Lorentz invariance by replacing the Laplacian by the wave operator. So we first observe neither field equation. Well, we have only talked about the field equation, but if you look at this here, you have the same. Yeah, you see obviously that if you have the del operator here, this doesn't involve a time derivative. This cannot work to get something which is Lorentz invariant. Neither field equation nor equation of motion is Lorentz invariant. So they must be modified if we want to fit them into special relativity. Try to modify them. In the following way. So I here just replace the Laplace operator by a wave operator. Then I have something which propagates with a speed c. Yeah, the c is coded into this operator. Yeah, the added term is minus 1 over c squared d by dt squared. So that's how the c comes in. And this I can also make into a Lorentz invariant equation if I write it not just with 3 components, but if I invent a 4th component, which is, so I make this 3 vector into a 4 vector, and this also. And, well, we have already learned that we always have to replace the time coordinate by proper time. So my natural guess would be to write this in this way. The tau squared, proper time now, x mu, and mu takes values, I try to avoid mu in equations where the mass density occurs. Rho takes values 0, 1, 2, 3. And then I have minus ms, and this is now d rho phi. These equations are indeed Lorentz covariant. Yeah, of course. This by itself, it's not obvious what I mean by this. To give a meaning to this sentence, I have to tell you how the phi and the mu, and well, it's obvious how the x rho changes. Yeah, that's defined directly in terms of the Lorentz transformation. But I have to tell you how the phi and the mu change. And what I mean is these equations are Lorentz invariant if phi and mu are invariant scalars. Yeah, if I do not change them when I make a Lorentz transformation. If I keep the same functions on space-time, provided phi and mu are Lorentz invariant. So the last remark before I stop, and then we can think together about this over the weekend. Now the question is this a reasonable assumption? So is it reasonable to assume that the mass density and the gravitational potentials are invariant scalar fields, independent of the observer? Well, actually, you should be able to answer this immediately. We have discussed it half an hour ago. Mu is the mass density. is it reasonable to assume that the mass density is a scalar invariant? That it's the same for all observers? We have discussed this already. Yeah? Mass density is mass divided by volume. And we have discussed that the volume is not Lorentz invariant. It changes if I go to another inertial system. So, well, these are equations which are Lorentz invariant. So from a mathematical point of view, I might say this is fine. But if you think of mu really that it has a meaning of a mass density, then the assumption that it is Lorentz invariant is just idiotic. Yeah? It's just a contradiction to what the physical meaning of this thing is. So that's the first thing which tells us that that's probably not a good idea to do it in this way. And the second idea is that we have learned from relativity that mass is only a particular form of energy. So it does not sound particularly promising to have only the mass density here. Why not the other energy forms? So you would replace this by the energy density. But the energy density is not a scalar invariant either. It is described by this energy momentum tensor, by a thing with two indices. And then it would come to the point that it would assume, well, it's not a good idea to have a scalar here. I should have a thing with two indices here. And then we are on the way to describing the gravitational field by a thing with two indices. And that's what we do in general relativity. So that was very briefly a lookout what we will do at the beginning of the next section. So we will see that this doesn't work. This doesn't work. We have to do something else. And we will discuss this at the beginning of next lecture, which will be on Friday, I think, right? Because on Thursday, I think, is Ascension Day. So this is a holiday here in Bremen also, as far as I know. So we will have the tutorials, of course, on Wednesday. But the next lecture will be on Friday, if I'm not mistaken. Okay, have a nice weekend.